Okay, I think we are going now. All right, so complex zeros of polynomials. Let's start with this whole complex number thing. Make sure we're still good with those. All right, so as you've seen before, complex numbers are numbers that kind of come in two pieces. They have a real part and an imaginary part. And they're written like this. A plus bi. And the A is the real part. And the I is the imaginary part. All right, now, imaginary numbers. Does anybody remember where those come from? How do we end up with imaginary numbers? Yeah. Go ahead. Square rooting negative numbers. Right. So, like if I tried to do the square root of -4, okay, normally we would say, oh, you can't do that, right? You can't take the square root of a negative number. In fact, when we were talking about domains earlier in this class, we talked about that a little bit. Square roots are one of those things we had to be careful of. You can't square root a negative number. Well, the reason that we were saying that was because we were working within the real number system. So when we talk about a domain of a function, we're talking about just real numbers. What's the domain? If I had asked what's the domain involving imaginary numbers, we could actually expand that out a little bit, but we're not going to go there with that. In any event, the square root of -4, square root of 4 is 2, but the square root of -4 then would be 2i. And when you break it down, really it all stems from the square root of -1, which is just I. So that's kind of the definition of I. Like, where does I come from in this whole thing? Well, it's the square root of -1. So we're going to look at that. When we come up with some of these complex roots, we're going to be dealing with square roots of negative numbers and pulling them out that way. Okay. I think my Algebra 2 class, if you had me last year, I talked about this a little bit, where the name imaginary comes from, because it's really confusing to a lot of students. Like, why do we call them imaginary numbers? Because they obviously exist. We use them, right? Well, the reason they're called imaginary is because the mathematicians who are first looking at this stuff, they didn't know if they were real or not. They were just theorizing that they were real. They thought maybe they were. So in all of their proofs, all of their papers that they were writing and submitting to, professors and stuff like that, they kept referring to them as imaginary numbers because they still weren't sure. Well, later on, it was proven that yes, they do exist, and we can work with them and use them and all of that. But the name imaginary had been stuck to them for like 100 years, and so people just kept referring to them as imaginary because it was like the common thing to call them, because that's what people were used to calling them. And so as time went on, we still call them imaginary numbers, even though they have uses and that sort of thing, but we just refer to them imaginary even though they're real. So it gets kind of confusing in the whole verbiage thing. Yeah?
What even proves that a number does or does not exist?
That's a very complicated question. I cannot answer that, but you can. All right. Anyway, that being said, let's move on. So that's a complex number. So we're going to have roots that will come out as being complex. Okay. So the fundamental theorem of algebra takes this idea and what we talked about yesterday and puts it together. If we allow ourselves to use complex numbers, not just real numbers, but complex numbers too, then the degree of a function, or the degree of a polynomial, is equal to the number of the roots that you'll have. Basically just that statement. A polynomial of degree n has n complex roots. Now remember when we were talking about real numbers? Okay, real zeros. We said that a polynomial's degree was at most how many it could have, right? Remember that polynomial investigation we were talking x-intercepts? We said the degree was always the maximum number of x-intercepts it could have. So it might have that many, but it might have less, right? Well, if we allow ourselves to look at complex numbers, which is imaginary, real, all of it together, then the degree is always exactly the same. Okay? Those x-intercepts are only the real solutions. It's not all the imaginary ones. So you're only getting part of the story there. But if you allow complex numbers in the game, then the degree and the number of roots is exactly the same. Okay? So what we can do with that then is, if we have some sort of a function that might involve some imaginaries, we can actually we will know how many roots we should have, and then we can go in search of all of them. So, give you an example. Let's say we've got x to the third minus 5x squared plus 2x minus 10. All right, and so just so we can kind of get the ball rolling here, I'm going to let you know that x equals 5 is a root. Okay, so we've got one of them. How many complex roots should this thing have total? 3. How many of them do I know right now? 1. Even though this is just x equals 5, that's technically a complex number. A complex number is imaginary, real, all of it. Okay, it's all of those. So this is one of our complex roots. We know that we have 2 more to go then, right? So let's do like we did yesterday. Let's do a little synthetic division. We'll take out the one that we know, and then see what we got left over. So bring down the 1. 5 times 1 is 5. Negative 5 plus 5 is 0. 5 times 0 is 0. 2 plus 0 is 2. 5 times 2 is 10. So, yep, that works. So, this is what we've got left over to work with now. So that is x squared plus 2. And in that little polynomial are the 2 other roots that we want to find. Yeah?
How did you know 5 was a root?
I just told you that. Like I said, for this one, just to get the ball rolling. Otherwise, what you'd have to do is the rational root test. Factors of 10 divided by factors of 1, and then like test them all out. But to save some time, I said, okay, I'm telling you, 5 works.
Yeah, but how did you know that?
How did I know that? Because I've done this problem before, and I know the answer. So what we got left over, x squared plus 2. Remember, we're trying to solve that yet, right? We're looking for zeros. So where is it equal to 0? That's going to help us get the roots. Now, as soon as you start to try and solve this, you're going to see the problem, at least doing it the old way that we were looking at it. If I subtract 2 to the other side, x squared equals negative 2. Well, how do we solve an equation with x squared in it like that? Square root both sides. And there's your imaginary number coming into play, right? As soon as you square root both sides of that, then you're square rooting a negative number. Okay? So, looking at real zeros, we'd say, can't do that, done. There's only the 1, just the 5. But if we're talking about complex, we can keep going with this then. So x equals the square root, or plus or minus the square root of negative 2. Now, written as an imaginary number, that would be x equals plus or minus the square root of 2i. Okay, because it's the square root of negative 2, we get rid of the negative, and that's the I, because the square root of negative 1 is I. All right, so we've got 1 real root, 2 imaginary roots, 3 complex roots altogether. Okay? And oftentimes they're going to be asked to write the solutions as complex numbers. Okay? So, I've got this one and these two. I'm going to write them as complex numbers for my answer. So I'd have x equals 5 plus 0i. Okay, that's this one. There's a real part but no imaginary part on that one. And then these guys down here, there's 2 of these, and those are, they have no real part, just an imaginary part to them. So x equals 0 plus the square root of 2i, and x equals 0 minus the square root of 2i. So degree of 3, we are able to find all 3 complex roots for that one. Okay? That's what that fundamental theorem of algebra says. Whatever the degree is, that's how many you should have when you're done. Yeah?
We have to write them out like that every time, even if it's 0i.
If the problem might ask you to write it in the form a plus bi, and if you see that, then yes. If no, then just leave them the way you had them. That's fine. Usually I don't care, but if the directions state it that way, then you're going to have to probably follow that. So, okay. So let's see if we can go the other direction with it, because I said that's kind of where I want to start before we get into doing more of this type of a thing. So if I give